Hi everyone and welcome to today's webinar, Steam Traps 102, entitled My Steam Trap is Good, Why Doesn't It Work? My name is Andrew Moore. I'm the Consulting and Engineering Services Manager for TLV in North America. And today I'm joined by David Adams, who is our Services Supervisor for the Gulf Coast, Texas region. So before we get started, we'll just go ahead and show you this disclaimer regarding the contents of the webinar and give you a few moments to read through that. All right, so this webinar is based off of an article written by Jim Risco, April 2015 Chemical Engineering Progress magazine, detailing all different reasons why steam traps are thought to be failed, but really it might not be the steam trap's fault. So we'll be really covering a lot of the topics in this article today. So why are we talking about steam traps? Well, if we look at a steam system, steam traps are really one of the keys to optimizing that steam system. So we have our steam generation and steam distribution, and the goal behind that is to supply dry steam to our process for optimal production. So we have our steam using equipment such as our turbines, our heat exchangers, and our tracing. We want to make sure that we're draining that condensate out of that equipment as quickly as possible in order to maximize efficiency. And also we want to be able to return that condensate in order to maximize our energy efficiency. And steam traps are really a key to all of that. So if we look at steam system optimization, there's really three different phases of steam system optimization. The first is going to be managing and optimizing our condensate discharge locations, or as we like to call them, our CDLs. Optimizing these will help us eliminate any problems that are caused by backing condensate up in our system, creating problems like water hammer or decreased production. Also reducing steam loss through leaking steam traps or open bypasses, which is a large energy waste. Next step in optimizing our steam system is going to be optimizing our steam using applications, our heat exchangers, our turbines, our steam generation, whatever steam equipment we have, but looking at how we can optimize that from a safety, reliability, and productivity standpoint, as well as recovering and reusing any heat that we can. Final step to steam system optimization would be to optimize our entire steam system by looking at our steam system balance, as well as our condensate recovery and our boiler feed water balance. So if we look at our steam traps, there's really three main functions of a steam trap. The first main function of a steam trap is to discharge condensate. If we're not discharging condensate through our steam traps, then we're not performing its primary function. Second function would be to prevent steam loss, hence the name steam trap. We want to make sure that we're operating efficiently and not losing steam. Third auxiliary function is going to be to discharge air and incondensables, which is going to give us a faster startup of our steam system, as well as help with things like our batch process equipment. So what happens when a steam trap fails? Well, if our steam trap fails closed, then we are backing up condensate and not able to get that condensate out of the system. That leads to problems such as water hammer, erosion, and production losses. Now, if our steam traps fail open, then we're going to have steam loss, which is going to be a waste of energy, as well as we're losing water and potentially creating a safety situation if that trap is discharging to atmosphere. We may also have problems with the trap failing closed due to incondensable gases such as air, where that's going to cause slower startup times, lower temperatures, and could cause condensate backup, which it could create water hammer and production losses as well. So let's take a minute and look at what a condensate discharge location is. So here we have our steam header, and we have condensate that's being formed in that steam header due to the radiant heat loss of that pipe. We want to be able to drain that condensate out, and that condensate goes ultimately to a return line through our condensate discharge location, and that steam trap is only a small part of that condensate discharge location. So a CDL is much more than just a steam trap, and it may include some of these components, such as an upstream blowdown valve, inlet isolation valve, Y strainer to help protect that steam trap from dirt and debris. Of course, the steam trap. We may see a bypass line around that steam trap, a check valve if we're going into a condensate return header, an outlet isolation valve, and a downstream blowdown valve. Now you may see all or some of these components at each one of your CDLs depending on what type of application you're draining, what pressure, and what your site specifications are. But it's important that whenever we're inspecting a steam trap that we actually take a step back and look at the entire CDL and see if there's any problems associated with any of these components on the CDL. So we often hear the term trap survey as well as CDL management. So what's the difference there? So some people may think, we have a lot of problems with our steam traps, or with our steam trap population, our steam system. We need to perform a trap survey. At that point, they award a contract to the lowest survey provider, who then goes out and surveys the steam traps. Any leaking steam traps are identified, and those are repaired first to maximize the return on investment of the cost of those steam traps as well as the cost of the survey. And there may be some short-term benefits seen, and things may not seem as bad as they were before. At this point, a lot of people forget about the steam traps, and it may be multiple years until another survey is performed and the cycle repeats. Now the problem with this is that there's no real progress being made in making the system optimized and helping you achieve a higher level of production. So you may see something like this with your year-over-year results, where you may see your leakage failure rate decreasing, but you have an increase in your cold and inconclusive steam traps. So overall, there's really no real improvement in the number of good CDLs that you have across your site. So what do you really want? What you want is to focus on reducing risk associated with your steam system and to optimize your production, ultimately to drive up the number of good CDLs. So what you really want to see is the number of good CDLs increasing over time through fixing those problems that are identified with each CDL. And there's a great article in the handout section written by John Walter from TLV about how to implement a sustainable steam trap management program. And this really lays the framework of what components are necessary in order to have a steam trap management program that is going to provide results that you want, rather than just performing surveys that really don't get you anywhere. You can also watch a webinar on our website by John Walter and Richard Newbegin about optimizing your steam system through steam trap management. Again, covering a lot of the points in John's article. So what should a CDL management program look like? Well, first of all, it needs to be simple, accurate, and most importantly, repeatable. This is going to be a program and not just a one-time event or one-time survey. And that really needs to start with accurately detecting CDL failures, and not just steam trap failures, but what is really wrong with that condensate discharge location, and identifying what that root cause is and try to eliminate that root cause. Ultimately replacing those defects with best practices, either being best practice steam traps or correcting the piping to make sure that it's best practice piping. And ultimately performing what we call zero reset maintenance, or ZRM. Basically resetting your failure state of your steam trap population down to zero, so ideally you have 100% of your steam traps and CDLs properly functioning. So one of the key components to CDL management is what TLV likes to call stewardship reporting. And what this reporting does, it allows you to track your progress made for your CDLs over time, and it also provides accountability and visibility to the steam trap management program. And as you have that long-term progress in tracking that, you're able to see long-term trends such as what applications, areas, or pressures maybe are performing well, or maybe which applications you're having repeated failures with. You can also see what manufacturers, models, or trap types are operating best for your site. So hopefully you can see some trends like this where your overall good percentage of steam traps is going up while your failures are going down. But then you can also see where maybe improvements can be made, where you see here an increase in inconclusive steam traps that may be hiding problems throughout your site. So if we look at the number of lifetime failures at a CDL, we may be able to see some trends. So here we have a site with several years of survey results, and we have a large group of steam traps that have 0 or maybe only 1 failure over the course of our survey history. Now these are obviously great traps with a good installation because they do not fail frequently. So this is where we want to be. We may have a group that have average to poor performance, and then we have these outliers over here. And these are what we would consider our bad actors. And generally what we see is 2 to 3% of the population is going to account for 10 to 15% of the overall site failures. So why is that? What's the problem with these CDLs? Do you ever see steam traps that are repeatedly failed, even if it's a brand new installation? And there's really no reason or visible evidence of why that steam trap failed. You often see operators who valve out a steam trap or bypass a steam trap because the problem cannot be identified. So here's an example here of a steam trap, and you can see there's been multiple steam traps that have been removed from this application, and there's repeated failures. In this case, it's really not the trap's fault. You can see this trap is installed at the midpoint of the header rather than below the header. So it's the application problem, not the steam trap. And the application problem has never been addressed, so the same thing is being done over and over with no real improvements. So now I'm going to flip it over to David Adams, who's going to start going through some common steam trap problems and mistakes that we see at different locations.
All right. So we have 4 different types of CDL problems that we're going to be talking about. The first one's going to be hot problems, which is where the trap has failed to open and is causing steam to be leaking. Next is going to be a cold problem. This is where the condensate cannot drain properly and is backing up condensate into the steam system. The other one is going to be hot trap, cold application. This is where the trap can be hot, but the application is actually cold. And here we have hot or cold trap, and this will depend on what type of trap it is and how it's installed. First, we'll talk about hot problems or traps that have failed open. The first one is going to be oversizing, where this is the size steam trap that we need, say on a trip or tracer, but what is installed is a big trap like this. Every steam trap is going to have a maximum capacity, and some steam traps are going to have a minimum required load. If your load is actually below that minimum required load, then you have a much larger trap than necessary, which can end up being more expensive. The steam may leak, and therefore you're going to have a shorter life. Next is going to be high back pressure. This is where the back pressure is relatively high compared to the inlet pressure. So when you have this case, you're going to have reduced trap capacity, which could lead to a cold trap and condensate being backed up. In the case of a disk trap, it won't be able to close, which will cause it to leak steam into the condensate return, which end up making the problem worse by increasing the condensate return pressure even more. And eventually you have where the downstream pressure is actually greater than the upstream pressure, and you no longer will have any flow, and you'll back up condensate into your steam system. So what are some of the causes of this high back pressure? System design pressure is one. One case of this is where you can have a condensate return line that is designed to be at 25 psi, and then they tie in a steam trap that's at 30 psi to go into there. This can cause issues with, say, disk traps that will cause them to leak. It also really puts you kind of on that edge of if any steam traps start leaking, you can be overpressured on that condensate return line. Vertical lifts are also going to add to the back pressure there, as well as undersized piping. If it's not sized to handle the correct load that is being given to it, then the pressure will increase. This happens a lot when plants have been expanded and the condensate return system has been neglected and not sized properly with the new expansions. You have high frictional losses from valves and turns and elbows and stuff. And some of the big causes are going to be leaking steam traps that can add a lot of extra steam into the condensate return line, as well as open bypass valves. So what do we do about this high back pressure? Well, you have two options. The first is going to be to raise the supply pressure. A lot of times this isn't feasible or really practical to accomplish. So your other option is to reduce the back pressure. One of the easiest ways to do this is to look at your steam trap population and replace those leaking steam traps, the ones that are blowing extra steam into your condensate return line. The other is identifying those blowdown valves that are open and closing those, and that can very quickly and easily reduce the back pressure in your condensate return system. Sometimes the answer becomes more complicated than that, and if you need help figuring that out, we can help with that. Next is going to be superheat. Superheat is a specific application where the steam is at a higher temperature than saturation. And depending on what steam trap you install, you can have issues with that. So if you select the incorrect trap type, such as an inverted bucket, superheated steam has a low condensate load, and therefore, along with the extra heat evaporating the condensate in there, you can end up where the bucket trap will not have any prime, and it will never be able to float up and close off. And this causes the steam trap to just leak through. In the case of a balanced pressure capsule with a thermostatic steam trap, the extra heat can cause that balanced pressure capsule to overexpand and eventually rupture, causing it to fail open and leak through. This ends up with a shorter service life as the steam traps get damaged by the leaking steam. You also have the steam leaks. Superheated steam leaks can also be very dangerous because sometimes they don't have a steam plume and you can't see them. Next, we have the incorrect set point as it being too high. In this case, we're showing a instrument enclosure with a tracing line going through it, and this is meant to keep the instrument warm instead of letting it freeze in the winter. But if your temperature adjustable steam trap is set too high, you'll end up giving too much heat into that instrument enclosure. It can end up damaging your expensive electronics, and that sometimes can even cause process issues. So, and this can also cause shorter service life of your steam trap with it leaking steam through there. Next, we're going to talk about cold problems, and this is where condensate is not being drained properly and can back up condensate into your steam system. So here, sometimes we'll see applications that need a large trap with a large capacity, but what we end up seeing is a tiny little trap meant for just drips and tracers. Like we mentioned, every trap has their maximum capacity, and if you have the load is above that capacity, you can't drain the condensate properly. And so when you can't meet that condensate load, condensate will back up, and this gives you poor process performance. Here's an example where we have a storage tank with a heating coil on it. Here we're going to have a 2-inch condensate outlet and a small 3/4 inch trap. This is just meant for drips and tracers, and it can't handle the load. So we look at the discharge of this trap, and it just looks like a garden hose with slightly warm water coming out of it, and you're not able to get the heating required to keep this storage tank at the temperature that you want it at, and that can cause all sorts of issues. So the fix here is to install the proper size steam trap with the capacity that you need in order to discharge all of the condensate. Pressure blocking, this is for mechanical style steam traps with orifices. This is where the buoyancy force ends up becoming less than the closing force on this steam trap. So when this happens, the trap is going to fail closed and back up condensate. It's not able to function properly. In the case of a free float style trap, it can't, that ball can't float off the orifice, allowing it to open and discharge condensate. So the condensate is backed up into your steam system, and this increases your risk of water hammer. So with this, we have to make sure that we meet the correct PMO when we install a steam trap. So the capacity and the PMO have an inverse relationship. So with a large orifice, you have a high capacity but a low PMO. On the other side, you have if you have a small orifice, you're going to have a low capacity and a high PMO. So here in this graphic, we can see that as the orifice gets larger, your discharge capacity goes up, but your PMO goes down. On the other side, as the orifice gets smaller, the discharge capacity goes down, and the PMO goes up. So you need to make sure that you're looking and being careful that you install a trap with the correct PMO, because the trap will not function, and you can keep replacing traps over and over and over again, but it's never going to work unless you have the correct PMO. The next thing we're going to talk about is stall. This is more common in heat exchangers that are modulated. In this case, we're looking at a air heater. And stall is where the inlet pressure becomes less than the back pressure, and you can no longer discharge condensate because you have a negative pressure differential across that steam trap. So the problem is you have, a lot of times you'll have your heat exchanger, as the control valve is fully open, you have that full inlet pressure going to it, and you can discharge condensate properly. But what will happen is you'll start to reach your process set temperature, and the control valve will start to pinch down. And eventually, it will close enough that the inlet pressure will become less than the discharge pressure, and you're no longer able to discharge condensate through a negative pressure differential. So when that happens, you back up condensate, and then your process set temperature will go down, and the control valve will then open back up because it needs to heat more. And it continues the cycle to where the control valve will open and close and keep swinging. This gives you to where you can't have tight control on your process set temperatures and uneven heating, and sometimes even not enough heating to where you can't reach the design temperatures that you're looking for. Another issue is this can end up causing water hammer. So the next question is, what do I do about this? How do I overcome a negative pressure differential when this occurs? Well, you need more than a steam trap. So we have a steam trap and steam motive pump combination here. Under positive pressure differential, it will work as a normal lever float style steam trap. As condensate comes in, it raises up the float, opening up the orifice, allowing condensate to discharge. But you get into that situation where the control valve pinches down and you get into a negative pressure differential. Well, the condensate keeps filling and will eventually lift the float up high enough that it hits the tripping point. This tripping point will open up the motive steam, and this allows high pressure steam to go through and push all the condensate through into the condensate return and function both in positive pressure differential and negative pressure differential. This is a very, very, very brief and simple look at stall. If you want to learn more, Jim Risco wrote an article that was published in November 2004 edition of Chemical Engineering titled "Steam Heat Exchangers Are Underworked and Oversurfaced." You can also find this article in the handout section of this webinar. We also have a webinar on our website called Common Refining and Petrochemical Steam Application Problems. This goes over stall in depth, and is a really good explanation of how this happens and how you can overcome that. Our next problem is going to be the incorrect set point low. Again, you have this instrument enclosure where the temperature adjustable steam trap, but in this case it's adjusted too low, and it backs up condensate too much, and it's not able to provide any of the heating that you need. So this can cause the condensate to back up, possible freezing in both the tracing line and in the instrument enclosure, damaging your instruments, and you can also have low process temperatures. Next is going to be air binding with thermodynamic steam traps. As air starts to go into these disc-style steam traps, the air acts in a similar way to the steam, and it causes the steam trap to shut. Well, the air gets on top of that in that control chamber and will end up holding that disc shut. But different from steam, the air does not condense and is slow to bleed through into the discharge. And this causes it to fail closed and not be able to discharge condensate, which causes it to back up into your steam system. Also on startup, you have your entire steam system is filled with air, and you need to get rid of that air as quickly as possible. The thermodynamic steam traps aren't going to do a great job of this because they'll air bind, and it takes a while for them to burp out all of the air. So what do we do about this? Disc traps are very versatile. They come in at a good price point, and they can be really good steam trap for you. One way to do it is with a rough surface on the disc. This creates tiny little leak paths for the air to leak through into the discharge and prevent air binding. The problem with that is that it also turns into leaking steam during normal operation, so your functional steam loss as the trap operates goes up. It also can lead to a shorter steam trap life. So here we have TLV's paradigm line of disc traps, where we have this bimetal ring on here, and when it's cold, it's going to hold the disc off of the seat, but as it heats up, it will expand and fall down this chamfer here and allow the steam trap to open properly. So here we see the air comes in and is able to flow through the trap without air binding, but as the condensate flows through, it'll start to heat up, and that bimetal ring expands, dropping down, and when the steam finally comes, then it's able to shut properly and seat more efficiently. Next, we're looking at dirt and debris. This is going to be really common in steam systems where we have steam systems are just dirty. Some of the refineries I go to are over 100 years old. It's just inevitable that you're going to have dirt and debris in your steam system. And this dirt and debris will find its way to the lowest points in the steam system, which ends up being where the steam trap should be installed. So it will end up clogging the strainers and the trap orifice. This causes the traps to fail closed, and of course condensate to back up and increases your risk of water hammer. So what do we do about this? We know that the dirt is inevitable, this debris is inevitable, so we have to design our CDLs, or condensate discharge location, to make sure that they can handle this dirt and debris properly. So again, we're going back to our picture. This is what the ideal setup looks like. It's got the proper size drip pocket, and it has this little area in the bottom here that will allow the dirt to collect. Periodically, you want to open up this valve here to blow that down. But what this allows is that relatively clean condensate can get pulled off of the side here and go down to your steam trap. The next thing is you have your upstream blowdown. This is another place where you can have the dirt collect and blow this down occasionally to get rid of that dirt before it gets down further downstream into your strainer and steam trap. Next is you have your strainer. The strainers are really great at catching that dirt and debris before it gets into the steam trap and allowing that to work better. Eventually, though, they will end up clogging, so it's good idea to have a program in place to blow down your strainers fairly regularly to make sure that they stay clean and not clog up. Next, we're going to have valved out, and this is going to be where the inlet or outlet isolation valve is closed. This makes it so where we can't identify the true condition of the steam trap. It doesn't have any steam to it, so we don't know if it's good or leaking or maybe even plugged. But condensate is not drained. And this leads to, of course, condensate being backed up into your steam system and all the bad things that we've been talking about. So why is a valve, or why is a trap going to be valved out? It seems kind of silly looking at it on the surface, but sometimes what happens is the steam trap is blowing, it's causing water hammer downstream, or it's leaking to the atmosphere to causing a safety issue. Also, the operators come by and they close it and they fix the leak and they solve the water hammer. But they've also created a cold CDL that backs up condensate. Sometimes the steam trap is replaced, but it's never commissioned. And so you install a brand new steam trap, that's awesome, but the steam traps are never, the isolation valves are never opened and allows the steam trap to operate properly. Sometimes the isolation valves are just shut and then forgotten about. It gets shut at one point, and then the new shift comes on and they didn't know it got closed, and eventually it just gets forgotten, left that way, or not understanding trap operation. Sometimes, especially with free flow style steam traps, will be discharging condensate and flash steam, and this leads some people to think that it is leaking, so they close the isolation valve and take that trap out of service, when in reality that flash steam is normal and how it's supposed to work. So what we want to encourage you to do is identify the root cause of why that steam trap was isolated, and then fix that and restore that trap to operation and allow those steam traps to operate properly and discharge that condensate. So next I'm going to turn it back over to Drew, and he's going to talk about hot traps and cold applications.
All right, thank you, David. So this section we're going to look at applications where the steam trap may be hot, steam trap may test as good, but we still have problems with condensate upstream of that steam trap in our equipment. So the first application we're going to look at is an application we call group trapping. And here you see 4 air coils in series, and they're all draining to a common steam trap. Now this may look like an okay application, but there's some hidden problems we may have. So with this type of application, we have multiple pieces of equipment draining to a single steam trap, and what's going to happen is we're going to have an imbalance of loads and pressures across each one of those pieces of equipment. In case of an air coil, we're going to have less of a condensate load on our last coil and a higher condensate load on our first coil, and a different pressure drop across each. This results in the last coil draining condensate because it has very little load and very little pressure drop, and condensate's going to back up in the other coils. So we're going to have a decrease in temperature of our air or our process because we have backed up condensate. And some people may think that they're saving on this installation because they're only installing 1 steam trap rather than 3 or 4, but really it's just causing problems with your production. So here you have a hot trap that may test good, the steam trap may operate fine, but you have a cold production process problem, which is probably more serious. So can you spot the problem here? Here we have multiple steam traps that are draining tracer lines into a common manifold. And this may be hard to identify, but you have multiple tracing lines draining to common steam traps. So again, here we have 2 pieces of equipment, or 2 tracing circuits, going to 1 steam trap. One of these circuits will be able to drain, while the other backs up condensate because there will be different loads and different pressure drops across those circuits, potentially leading to decreased temperatures in our process line, which could cause some thermal maintenance issues. So solution to group trapping, it's relatively simple. You need to have individual steam traps on each piece of steam using equipment. In case of an air coil, each section of your air coil needs a separate steam trap, where with tracing, each tracer circuit needs to have its own steam trap to optimize its heating abilities. Next, we'll look at applications known as steam locking. And there's a few different types of steam locking applications. But in general, this is where steam enters the trap before condensate. And because the steam trap sees steam, it's going to close, and we're not going to allow condensate to get into the system. In this animation, you can see there's a lift before the steam trap, and that steam has to condense before condensate can work its way up into the steam trap, allowing condensate to get out of our system. So with this type of application, our trap is installed above the lowest point in our system. Condensate wants to drain downhill. It wants to gravity drain. It doesn't want to go uphill very easily. So we're going to have a problem getting condensate into that steam trap. And it's going to result in a backup of condensate into our equipment, causing heating problems. So again, the trap may test hot, it may test as good, but we have a problem with heating. So do we see a problem here? So here we have a steam trap manifold collecting condensate from multiple tracer lines. And on the left, you can see this tracing line has a loop in it, which is creating a steam lock immediately upstream of the trap. That could back up condensate and cause a low process temperature in the line that we're tracing. Now, if we look at the circuit on the right, it looks like we have gravity drainage all the way to the trap, which looks good. But if we take a further step back, we actually see that we have a lift further upstream, which is creating a steam lock, which again is creating a problem with heating our process. You also see steam locking on applications that have long runs of horizontal pipe, as well as anywhere where you have maybe bends or loops in your piping or tubing leading up to your steam trap. So do you see the problem here? We have a long run of horizontal pipe leading up to our steam trap, and you can see we have an open bypass near that steam trap to try to alleviate that steam lock because we can't get condensate out of the system due to the steam lock. So how do you solve a steam lock application? Well, one way to solve it is to use an external bypass which bleeds off that steam, allowing condensate to drain to your trap. Now, the problem with this is if that valve is closed, well, you have a steam lock. The other problem is if you open it too much, now you have wasted steam and you're operating very energy efficiently. So this right here is more of a band-aid than a solution. The best solution is to put the trap at the lowest possible location to allow gravity drainage, but that's not always practical given some of your steam using equipment. So sometimes you need to have some type of steam lock release in order to make these applications work. So TLV, we like to solve that by using our free float steam trap, and then we manufacture this with a continuous fixed discharge, which eliminates the variability of a bypass valve, and this gives us a very small steam bleed through this trap to release that steam lock of just a few pounds an hour. So it is an energy deficit, but it's a necessary deficit that we need to pay in order to have proper heating to our production, which is probably much more valuable than a few pounds of steam an hour. Next problem we're going to look at is where our steam trap is insulated. And you might look at that and say, well, what's wrong with this? Well, there's a few problems. One, sometimes it can be very difficult to find the trap. Where is it? It's often hidden under insulation and no one knows that it's there, which makes it very difficult to inspect. Also, certain types of traps are going to have a very high level of condensate backup if we insulate that trap. Some steam traps need to naturally lose and radiate heat in order for them to operate properly. And if we don't allow that trap to lose that heat, we're going to be backing up more condensate than we want to and potentially causing backup into our equipment, leading to low process temperatures. So again, our trap may be hot, but we may be backing up condensate into our equipment. So here's a fun game. Where's the trap? So here's a trap that we came across, and it's very difficult to identify what trap that is, what type of trap that is, and it's very difficult to inspect if that trap is operating properly because it's completely insulated. So what traps should I insulate and what traps shouldn't I insulate? So we can look at this table. So in general, mechanical style traps such as TLV's free float or lever floats are completely safe to insulate because they operate on a principle of buoyancy. They do not require the radiant heat loss or condensing of steam in order to function. Now, inverted bucket traps, you can insulate those, but insulating those to a high degree could reduce your cycle times, which could back up condensate. So while it may be okay, you want to be careful with insulating your bucket traps. Thermodynamic traps require radiant heat loss out of the control chamber in order to cycle. So those you definitely do not want to insulate. Same with thermostatic traps such as balanced pressure thermostatic capsules or bimetal traps. Those are temperature sensitive, and insulating those will hold in more heat, reducing the cycle time, increasing your condensate backup. So what's the solution for insulating traps? Well, really you want to insulate upstream and downstream of that trap in order to maximize your energy efficiency, but you do not want to insulate the trap itself, so that way it can be identified, it can be tested, and ultimately maintained and function properly. All right, next type of application is going to be what we call double trapping, or sometimes you hear it as series trapping. Here we have two steam traps, one installed downstream of the other. So the problem we see here is that it creates an intermediate pressure between those two steam traps, which the second trap is going to have a very decreased capacity because now we have a very low pressure differential across that trap. And what that can do is back up condensate into our equipment. So how does this happen? How do we get two steam traps installed in series like this? Well, sometimes steam trap number one is leaking, so someone installs steam trap number two downstream of it to stop the leak. This is obviously flawed thinking. The second is steam trap number one is not noticeable because it's insulated or it's installed high or remotely, so it's just not noticed. Or sometimes number three, steam trap number one is mistaken maybe for a strainer or check valve or another piece of piping, so steam trap is installed downstream of it. So obviously the correct way to handle this is to remove one of the steam traps and make sure that the other steam trap is operating properly to fix this CDL problem. All right, improper drainage. So you may see locations where you're not taking condensate off the bottom of your steam header or off the bottom of your equipment. So what this is doing is basically backing up condensate into your header or into your equipment, and you're not fully draining it. Or you have a steam distribution header with a very small takeoff going down to a steam trap rather than a properly sized condensate collection pocket. In that case, a lot of your condensate is passing over that takeoff, not allowing you to have full drainage. So on here, really it's inadequate piping design, which is leading to the backup of condensate or the incomplete drainage of condensate. And in these applications, we're going to be having a risk of water hammer by having all of that condensate backed up in our equipment or our steam headers. And here the trap, it may test good, it may look hot, but we're going to be backing up condensate because of an inadequate design. So do we see a problem here? So here we have a steam header flowing steam through this elbow. We have a takeoff going to a trap, but we have incomplete drainage at this location. And again here we have our condensate flow, and then we have a takeoff coming off the side of that header, and you can see that we're pouring condensate out of that steam trap, and we're not able to drain all of that condensate out of that header as well. So we really want to make sure that we're following proper piping practices by having a properly sized drip pocket to allow that condensate to fall out of our system so we can drain that out. So we should be looking for something like this rather than the previous images. All right, so now we're going to switch gears and look at applications where the trap may be hot or the trap may be cold. It really depends on the application. So first thing we'll look at is steam trap orientation. So here we have a free float steam trap which is designed to be installed in horizontal piping. In this case, it's been installed in vertical piping. Now we'll be able to drain condensate out of that trap initially, but that float is not going to be able to properly seat on the orifice, eventually leading to a steam leak and energy inefficiency. So with this, it's really a misinstallation of the steam trap. So this could be a brand new steam trap, but it's never given the opportunity to function properly. And depending on the type of trap, it could leak or it could be cold if we have it installed improperly. So we can look at a thermodynamic disc trap. And if we install this with the disc vertically rather than horizontally, this trap is actually still going to function normally. It may have a slightly shorter service life, but we can still operate this normally. Same with a thermostatic steam trap, which operates on principles of temperature. We can operate that in vertical piping even when it's designed for horizontal piping with little side effects. So these traps are largely unaffected by that orientation. And vertical installation may give us a free draining type application where we're not backing up any condensate on shutdown, but horizontal installations are definitely going to give us the longest service life. So we can look here at this chart, and one note on this is that these are general trends, and the actual condition of your steam traps may vary based on the trap type and the installation. But you can see, in general, mechanical style steam traps such as free floats, lever floats, or inverted buckets, when installed in improper orientations, are going to tend to leak. Thermodynamic and thermostatic traps are generally going to be okay if they're installed outside of their intended orientation. If we look at traps that are installed upside down, lever floats and free float traps, they may fail, they may leak, or they may be cold, depending on condensate load and other factors. But you can see different failures with those if they're installed upside down, whereas a bucket trap is going to fail closed upside down. And while thermodynamic and thermostatic traps may function upside down, it's definitely not advised because of shorter service life. And then traps installed backwards, mechanical traps and disc traps are going to tend to leak when installed upside down, and thermostatic traps may still function to a degree, but the discharge temperature is going to be much lower than what's intended, which may back up condensate. So do you see a problem here? We have condensate going down to our trap, and that trap is actually rotated 90 degrees. This is a free float trap, so that trap is not allowing the float to sit on the orifice, creating a steam leak. Here we have steam supply going to a turbine, and our steam trap is a disc trap, and that disc is upside down. So while this may operate, it's not going to give us best performance or best service life. So we want to make sure that we correct that. All right, next we're going to look at bypassed steam traps. So here we have our condensate discharge location, and we come across a trap with the bypass open. So what's the problem here? Well, with a bypass open, we are getting condensate out of our system, but now we're doing it very energy inefficiently. That open bypass is going to be blowing a lot of steam along with getting any condensate out. And we cannot accurately judge the condition of that steam trap because we have this bypass open. We don't know if this trap is leaking, or we don't know if this trap is cold. And open bypasses are usually a signal that there is a hidden problem either with the trap or with the CDL. So that's a definite key sign and should be a red flag that there needs to be further investigation into this piece of equipment to identify what's really going on. So why are bypasses open and why are they left open? Well, common reasons are the steam trap is blocked and you can't get heat into your process, so the bypass is open in order to drain condensate. Another reason is that the trap is undersized and you're backing up condensate, so the bypass is opened to provide additional capacity. Sometimes it's open because you have a steam lock and you need to alleviate that steam locking condition, so bypass is opened. Or you're pressure blocked where you have the incorrect steam trap for that application and you can't drain condensate. Also group trapping, where you're getting insufficient heating into your equipment because you only have one steam trap or you need multiple. Or you're running into a stall scenario where you can't get condensate out of your system and into your condensate return line, so you may open a bypass to atmosphere to drain that condensate out of your system. So with all of these, it's important to identify the root cause of why is this bypass open and correct that root cause to make sure that you're optimizing your equipment. All right, so now we'll look at improper trap types. So here we have a condensate discharge location on a steam header, and we're using a bimetallic thermostatic steam trap. Now with this, it's the incorrect type of trap for this application. Now the application looks good, the installation is fine, but it's definitely the wrong type. This is going to result in backed up condensate into our steam header, which can result in things like water hammer. So we want to make sure that we're selecting the appropriate steam trap for that based on your site standards and also manufacturer recommendations to make sure that we're not putting a trap in an application that it's really not meant for. Next we have improper trap type, where we have continuous drainage, where we may actually want a trap that is subcooling condensate. So in this case, again, the installation looks good, but it's the wrong trap. And we're providing, in this example, too much heat to our instrumentation, which could damage our instrumentation and cause an upset in our plant. So again, we want to make sure that we're selecting the correct trap based on our standards and manufacturer recommendations. So we've talked about a lot of different CDL problems, and one thing that TLV likes to provide is what we call a standard and trap application review. So here we help you select the best models for each one of your applications based upon your site specifications, your unique applications, and what your preferred trap technologies are. So from this, we will help you develop a series of best practice installation diagrams based on your site piping requirements and practices to make sure that every condensate discharge location receives the correct trap as well as has the correct piping requirements in order to make sure that we're avoiding any of these problems that we've talked about. So just to wrap things up, we'd like to thank you for joining us. You can reach our consulting and engineering services group in North America at 1-800-TLV-TRAP or email us at ces@tlvengineering.com. And if you're outside of North America, you can always reach us at one of our 14 global offices that are nearest to you. Also, you can visit our website where you can find our online calculator, the technical articles that are attached in the handout section, as well as many more, as well as webinar recordings. This webinar recording will probably be posted next week, but you can also find all of our other webinar recordings. So with that, I'll turn on my webcam. David, do we have anything else?
No, that's all we have for today. If you did ask a question in the question box, it'll be answered individually, and we'll reach out to you if it requires further explanation.
Excellent. All right, well, thank you everyone for joining us. Please join us in 2 weeks when Tracy Snow and Justin McFarland will be presenting on steam trap or refinery steam applications and problems commonly seen. So hope you have a good weekend, and thank you again.